Hi everyone, my name is Zifeng Kang from Johns Hopkins University. Today I'm happy to present our work called Proto, measuring client-side prototype pollution vulnerabilities of 1 million real-world websites. First, what is prototype pollution? Prototype pollution is a relatively new JavaScript vulnerability type discovered in 2018. It involves polluting a base object's property, such as object.prototype.toString. Such property further opens up a backdoor for the adversaries to inject malicious code, and it will cause further consequences. Prior works also study prototype pollution vulnerabilities and how to detect them. However, there are two main issues. First, the consequence of prototype pollution is unclear. And secondly, they target at server-side applications only, but they do not study client-side prototype pollution. Speaking of consequences, what are they? Consequences are further vulnerabilities or damages caused by prototype pollution after the adversary has successfully injected her malicious code through prototype pollution. Examples could be cross-site scripting, cookie manipulations, and URL manipulations. Now the question is, are those consequences caused by prototype pollution really practical in real-world websites? The answer is yes. Let's see an amazing, motivating example leading to cross-site scripting. Actually, this example is different from traditional cross-site scripting because the exploit involves the parts _Proto bracket K that can trigger the prototype pollution vulnerability. And then the prototype pollution will further lead to cross-site scripting. The example is about the zero-day vulnerability of borderbots.com. Borderbots.com is an authorized dealer of Malibu boats. After we report this vulnerability to the owners of BorderBoats, they haven't replied to us, and they haven't fixed that vulnerability. The exploit is as follows. borderbots.com/default.asp _Proto bracket K equals to some malicious script, as well as some other parameters called and page equals to x all inventory and make equals to chaperone. Let's see how this exploit works in the real world. So we visit this exploit URL, wait for the page to load. What we see, yes, the borderbots.com has a pop-up window saying that it has already been exploited. This is exactly what we expect from the exploit code. And this is clearly a sign of cross-site scripting. We want to mention two main challenges regarding the exploits. First, we need to explore the sub-pages of this website. If we only visit the main page, the exploit will not work. Secondly, we need to append the correct parameters. If we do not do so, the exploit will not work as well. We can see that this page of this website is not being affected if we do not inject the correct parameters. So come to the explanation of that amazing example. Let us take a closer look in reverse from where the code is injected, which is where the cross-site scripting really happens. Inside this for loop, there's a cross-site scripting sync function, which is the dorm elements append function. Say that we can control this field, data bracket field, then cross-site scripting happens because what the append function is doing is it will append all of those codes into the dorm element. But the data object here is either constant or defined via AJAX from BorderBots. So how do we exploit this cross-site scripting? Namely, how can we take control of this data bracket field? The answer is through prototype pollution. Let's switch to the code snippet vulnerable to prototype pollution in the same website. In this for loop, there are basically two main iterations. In the first iteration, the variable p will be set as the __ proto __ as the adversary injected. Secondly, the O equals to OP will be executed. Note that the variable O here is originally an object. And for now, O will point to object of the prototype because in JavaScript, an object bracket __ proto __ will point directly to object of the prototype. In the second iteration, P will set as a key value K. Then after it, O equals to OP equals to J will be executed. This time, O bracket K, which is object of prototype.k, equals to the malicious code injected by the adversary. What does it mean in the end? We successfully pollute the prototype in JavaScript, which is object of the prototype.k equals to script alert exploited script. This is how prototype pollution happens. But how can it contribute to the cross-scripting? Let us look back at the code where cross-scripting happens. In this append function, data bracket field, which now is data bracket k, equals to script alert exploited script, the malicious code. How would this happen? So basically, data.k is not defined at the beginning. However, through the prototype chain mechanism in JavaScript, data.k equals to data.__ proto __ k equals to the object of prototype.k, which will be the malicious code eventually. So when the append function appends that malicious code to the DORM, cross-scripting happens. This example shows exactly how prototype pollution leads to cross-scripting. After seeing this consequence, we will talk about other consequences, such as cookie manipulation, URL manipulation, and more. Cookie manipulation involves document.cookie affected by a polluted property. A polluted property is a property being manipulated by the adversary that the adversary can take control of. The other one, URL manipulation, involves image.source, iframe.source, or script.source affected by a polluted property similarly. After that, we talk about our design of the Proto in order to detect prototype pollution vulnerabilities and its further consequences. The intuitive idea is to utilize joint taint flow analysis. Here, we list adversary-controlled inputs as well as the vulnerable code snippets here. In the for loop, during the first iteration, the O equals to OP will be executed. This is the first sync function for prototype pollution, namely object lookup. In the second iteration, the O bracket P equals to J will be executed. This is the second sync function of prototype pollution, namely value assignment. So we list it right there. The last sync function is the cross-scripting sync function. In this example, it is the append function. Then we talk about the data flows. The first part, __ proto __ of the adversary controlled inputs will flow into the variable P in the sync function 1. This is the first data flow. The second data flow is K flowing into the variable P in the sync function 2. And the last one, the malicious code part, flowing into the variable J in the sync function 2, and finally flowing into the cross-scripting sync, and then call the cross-scripting example that we have shown before. The term joint taint flow consists of all of those three data flows, and the Proto will perform dynamic taint analysis on the top of joint taint flows. Next, we talk about our system architecture. It involves two main modules. First is called joint taint flow analysis. Second one is result validation. After Proto iteratively crawls each website, it will use joint taint flow analysis module to analyze and generate the joint flows as well as the exploits for the proliferation as well as the further consequences. After the results validation, Proto will generate a technical report to report to the corresponding website owners if there are any proliferation vulnerabilities or further consequences exist. As for the joint taint flow analysis module, there are basically two main parts. The input exploit generator will generate inputs for the dynamic taint engine to do taint tracking and to discover joint taint flows. Then the taint engine will provide sufficient information for the input exploit generator to generate next step inputs or the final step exploits. This procedure will repeat for several times. Then the generated flows and exploits will be fed into the result validation module. Inside it, there is an exploit validation part, which is responsible for validating the exploits not only for proliferation, but also for the further consequences, such as cross-site scripting. The other part is defense analysis, which is responsible for analyzing how real-world websites defend against proliferation vulnerabilities. This is our overall system architecture. After that, we will talk about our evaluation results. In general, our evaluation consists of 6 main parts: the measurement results, the comparison with prior works, the performance, false negatives, code coverage, and defense. But due to limited times, we will only cover the measurement results in these slides. For other parts, please read our paper. We will talk about our measurement results in this slide. Proto has discovered lots of zero-day exploitable vulnerabilities. The total number is near 3,000 out of top 1 million real-world websites. After we report all of those vulnerabilities to their corresponding website owners, many of them have been fixed. The number is more than 200. After that, we break down the vulnerabilities according to the consequences. There are 3 main categories in this table, namely cross-site scripting, cookie manipulations, and URL manipulations, with the URL manipulations being the most prevalent one. Then we provide several vulnerable domain examples. The selected domains are webly.com, cnet.com, and mckinsey.com. The table also lists their rankings, status, and exploit codes. Note that cnet.com and mckinsey.com have already fixed the vulnerability of proliferation after we report to them. mckinsey.com even provide positive feedback, confirm our discoveries, and fix the vulnerability in a very short period of time. This slide is about breakdown by the sources and things. For the sources, there are joint flow sources, namely URL search, URL hash, URL and URL search, cookie, and message, with the URL search being the most prevalent one. As for the sync part, the consequences have multiple sync types, namely cross-site scripting has 4 sync types: inner HTML, append, eval, and such attribute. Finally, we come to the conclusion. Proto is the first large-scale measurement of client-side proliferation and further consequences. Next, Proto discovers 2917 zero-day exploitable vulnerabilities, 48 leading to cross-site scripting, over 700 leading to cookie manipulations, and over 800 leading to URL manipulations. We responsibly reported all the discovered zero-day vulnerabilities to website owners, and many of the vulnerabilities have already been fixed. Thank you.